Dsauce, Daniel here. And where is down? Seriously, it's a pretty easy question that you should be able to answer, but how do you know? Well, you might say, I know where down is. It's that way. But to someone on the other side of the earth, their down is my up. So to figure this out, let's first drop this pencil. Well, that was odd. Now, obviously gravity was at work here, but how does gravity work in the way that it does? Why do things fall to the earth? And where are falling things going? To figure this out, let's first turn the sun into a black hole. Now, how would we go about doing this? Well, you see, every object has what's called a Schwarzschild radius. Now, a Schwarzschild radius is the radius that an object needs to get compressed into in order to form a black hole. For the sun, this is about 3 kilometers, while smaller objects, like the Earth for example, have smaller Schwarzschild radii. Now, for the Earth, this is about 1 centimeter. Now, since we physically cannot do this, take a second to think about what would happen if we were to do such a thing. Would the Earth be flung out into intergalactic space? Would the Earth be gobbled up by the sun? Or nothing? Nothing would change. Of course, things would become a lot darker and colder. However, the Earth and every other planet in the solar system would remain in their current orbits. You see, by shrinking the sun to the point where it becomes a black hole, we didn't change the direction of down for the planets. They're always being pulled towards the center of the sun, and by shrinking the sun, we didn't change where the center is. But also, we didn't change the strength of gravity either. Now, how can this be the case? Now, mass is typically described as how much matter is packed within an object. And while this is all well and good, for our purposes, we can also define mass as how easy or how hard an object is to accelerate. So to show you this, I have these two Fiji water bottles right here. Now, right now, both of these bottles have zero motion relative to me. Slapping around this empty bottle of Fiji water is relatively easy. It doesn't require a lot of force. Whereas slapping around this full bottle of Fiji water, tempting as it is to drink, requires a lot greater force to keep it going. Now, why is this the case? Well, you see, the full bottle of Fiji water has more mass than the smaller one, requiring a greater force to accelerate it. Now, according to Newton's second law, the acceleration of an object is directly proportional to the force placed upon it, and is inversely proportional to the mass of an object. And from this, we get the equation force equals mass times acceleration. Now, mass is an intrinsic property of matter. It doesn't change depending on where you are. You could be on the moon, on the Earth, floating around in intergalactic space, and you'll always have the same mass. However, mass does seem to care about what's around it. Mass loves company. Now, all things with mass are attracted together by a force that we call gravity. The feeling of gravity is just you and the Earth being attracted together. Now, giant things like the Earth exert the most obvious force of gravity. However, everything exerts a force of gravity, even this pencil. Fun fact, the amount of gravitational force that this pencil experiences from the Earth is the exact same gravitational force that the Earth experiences from this pencil. Now, Daniel, you might say, how is this possible? And I would respond with Newton, or Newton's third law for all you non-hip kids out there. Now, Newton's third law states that for every action, there's an equal and opposite reaction. And these equal and opposite reactions occur in interaction force pairs, where the direction of the forces are opposite of each other, but the force themselves are the same. Now, let's consider this pencil again. According to Newton's third law, the gravitational force that this pencil experiences from the Earth should be the same that the Earth experiences from this pencil. Now, Daniel, you might rudely interrupt again. How could this be the case? Every time I drop something, shouldn't the Earth violently shake, causing monumental damage that might even destroy the human race, or could even rip apart the Earth as we know it? And as wacky and cool as that sounds, That's obviously not the case. See, going back to Newton's second law, because the Earth is so massive, the acceleration that this force causes on the Earth is so small that the Earth will only move a very tiny amount in the time that it takes this pencil to fall to the ground. So let's do some math. Assuming that the mass of this pencil is about 0.1 kilogram, we can calculate that the force that the pencil feels from the Earth is about 1 Newton. Now, because of Newton's third law, the Earth would also experience about 1 Newton of force from this pencil. So as I drop the pencil, we can calculate that the Earth would move less than the distance of a proton in the time that it takes for the pencil to fall to the ground. So technically, the pencil didn't fall to the Earth. The Earth and the pencil fell together. Now, gravity is a law of physics. Why and how it works is one of the fundamental properties of the universe as we know it. Now, there are many other laws that the universe abides by, but one in particular, the law of conservation of angular momentum, is often overlooked as to how weird it can get. First off, here we have a particle that is rotating around a center point C. Of course, there has to be some centripetal force keeping the particle in orbit around point C. However, we can just ignore this for now. So what is angular momentum? Well, if we multiply the particle's mass by the particle's instantaneous linear velocity and the radius formed by the orbit around point C, then we have just found the particle's angular momentum. Now, according to the law of the conservation of angular momentum, the total amount of angular momentum of the particle will neither decrease nor increase. Now, what this means is that if we keep the mass of the particle the same, and we increase the radius that the particle orbits, then the velocity of the particle will have to decrease. Now, conversely, if we decrease the radius that the particle orbits, then the velocity of the particle will have to increase to conserve angular momentum. Now you see, angular momentum is a vector quantity, meaning that it has both a magnitude and a direction. Now, according to the law of conservation of angular momentum, both the direction and the magnitude of angular momentum has to be conserved. So what is the direction of something's spin? So I have this disk right here, and it's obviously spinning counterclockwise, right? Well, if I flip it over, keeping it spinning in the same way, it now looks like it's spinning clockwise. Now, what this means is that the apparent direction of a spinning object's spin, whether it's clockwise or counterclockwise, is completely dependent on the orientation of the observer. Now, in order to unambiguously differentiate the direction of something's spin, what we need is a tool that has no axis of symmetry in any of the 3 spatial dimensions. And luckily, we all have one of those built right into our bodies. Our right hands. Now, I can only really curl my right hand in one direction, like this. So if I have this disc here, and it's spinning counterclockwise relative to you, well, I can orient my right hand so that my knuckles are facing away from the center of the circle, and so that a point on the disc will travel from my wrist to my fingertips. We can find that my thumb will always point in the same direction regardless of the observer. Now, what this means is that the direction that my thumb is pointing in is the direction of something's angular momentum. And this is called the right hand rule. So here I have this wheel, and if we give it a counterclockwise spin relative to you, we can use the right hand rule to find that the direction of its angular momentum is up. Let's call this L positive. Now, if we flip the wheel over while keeping it spinning in the same direction, we can use the right hand rule again to find that the direction of its spin is now downward. Let's call this L negative. Now this seems intuitive, but you have to remember that this cannot happen without angular momentum being conserved. So, what plus negative L equals positive L? Positive 2L. So where did that positive 2L go? So let's look at this again. I have this wheel here, and it's spinning counterclockwise relative to you. Its angular momentum is positive L, and when I flip it over, its angular momentum turns into negative L by losing positive 2L to something. Now, to figure out what this something is, I'm going to take both of my feet off the ground as I flip the wheel and see what happens. So we got a counterclockwise spin on the wheel, and both of my feet are off of the ground, so let's flip it. So as you saw, that positive 2L went into me. Now the conservation of angular momentum is not actually why this spinning occurs. You see, if you were to do this at home, you would feel the bars on the wheel pulling and pushing on your hands, causing your body to rotate in the chair. Now, why is this? Well, let's first talk about tilt. Now, how am I going to make this wheel tilt? Well, that's pretty easy. All you gotta do is push down somewhere on the wheel. Now, the wheel is going to tilt, obviously, in the direction that I push on it. However, if we give this wheel a spin, and we push down on it somewhere, right here, it's not going to tilt down in the direction where I push on it. You see, all of the points on the wheel have some velocity prior to being pushed on. So, as I push down here, the wheel is going to tilt in this direction, but it's also going to continue on its path backwards towards me. Now the result of this is that the wheel tilts about 90 degrees past where I push on it. So let's look at this again. If we have a wheel that is spinning counterclockwise relative to you, and we push down here, it's going to tilt towards me. And if we push up on this side, well, that's the same as pushing down on this side, so it's also going to tilt towards me. And that was exactly what I was doing when I was flipping the wheel. So as I was flipping the wheel wanted to tilt towards me. However, I had my hands in the way, preventing it from tilting. So the result of that was that my right hand was pushed backwards and my left hand was pushed forwards. And this is what applied the torque on my body. And this is the physical origin of what we witnessed. Now this is a really cool concept. As I was flipping the wheel, I could feel the wheel pushing against my hands, resisting the flip. It was self-stabilizing. Now this is how a gyroscope can seemingly defy gravity. Or how a gun or a bow put a spin on the projectiles in order to make them more accurate. So with all this being said, if you ever find yourself in a situation that makes you feel emotionally unbalanced, put a spin on it, and you'll be upright in no time. And as always, thanks for watching.